The next talk, let me mention that there's a photo op. That means we're all going to have a photo taken, a group photo. Everybody has to come, no exceptions. And it'll be immediately after the talk at the front entrance to the building. So again, no excuses. Everybody has to come for the photo immediately after the next talk. And I'll check to make sure you're all there. Okay, so it's my pleasure now to announce the talk of Professor Yao, who is from East China Normal University, and he'll speak on contact processes on some inhomogeneous graphs and random graphs.
Trust the invitation and thanks for Michael's introduction. I feel very honored to have this chance to speak here at Yao. Today I'm talking about context processes on some inhomogeneous graphs and random graphs. The outline of my talk is as follows. First, I give a very brief introduction. Then I will talk about the three different models we are interested in recent years. Context process was first introduced by Harris in 1974. It is a model to describe the spread of diseases. There are two classical books concerning some basic definitions as well as some basic results. Both the books were written by Thomas Leavitt. The first book was published in 1985, and the second book was published in 1999. Let me give a brief introduction of this process. We consider a graph a connected undirected graph denoted by G. We denote by V its vertex set and denote by E its edge set. The context process cassette T is a continuous time Markov process. The state space of the process is the set of all subsets of the vertex set V. At each time T, each vertex is either healthy or infected. We use the notation cassette T to denote the collection of all infected vertices at time T. The transition rates are given as follows. Simply speaking, an infected site becomes healthy at rate 1, while the healthy vertex becomes infected at the rate proportional to the number of its infected neighbors. The proportional coefficient is denoted by lambda, which is the only parameter of the process. Furthermore, we use the notation cassette A to denote the process with initial state A. That is, at time 0, all vertices in A are infected, but the other vertices are healthy. This process has only one absorbing state, the empty set. That is, if at a time all vertices are healthy, then there will be no infected vertices from then on. Is this clear? The asymptotic behavior of the contact process depends on the parameter lambda. We see that the process survives if the infection will persist with positive probability. Otherwise, we see that it dies out. Furthermore, we can divide survival into strong survival and weak survival. Strong survival means that if you look at a fixed vertex, it will be infected infinitely many times with positive probability. The weak survival says that globally the infection will persist with positive probability, but locally every site will be infected only finite times with probability 1. That means the infection moves away to infinity, maybe New York, maybe somewhere else. By the monotonicity of the contact process, we can define two critical values. That is, we denote by lambda 1 the infimum of lambda that the process survives, and we denoted by lambda 2 the infimum of lambda such that the process survives strongly. Since the contact process survives strongly implies the process survives, we can get this inequality that lambda 1 is no larger than lambda 2. And on an infinite connected graph of bounded degrees, lambda 1 is strictly larger than 0, and lambda 2 is strictly smaller than infinity. So there are three phases. That is, the process dies out if lambda is smaller than lambda 1. The process survives weakly if lambda is between lambda 1 and lambda 2, while the process survives strongly if lambda is larger than lambda 2. Sometimes these two critical values are the same, but other times they are different. There are some known results. On the integral lattices ZD, the two critical points are the same. We denote their common value by lambda c. But on homogeneous trees TD, where D is larger than or equals to 3, they are different. So for the d-dimensional lattice case, there is only one phase transition. But for the homogeneous tree case, there are two phase transitions. An important property for the asymptotic behavior of the process is the so-called complete convergence theorem. We use CCT for short. That is, the distribution of the process converges to a convex combination of two special measures. One is the so-called upper invariant measure, and the other one is the trivial lower invariant measure. The coefficient alpha A is the survival probability. This property does not always hold. For the d-dimensional lattice case, it is proved that CCT holds for all parameter lambda, but for the homogeneous tree case, CCT holds for large lambda, that is, lambda is larger than the second critical point, lambda 2. And CCT does not hold if lambda is between lambda 1 and lambda 2. When lambda is smaller than lambda 1, the CCT holds trivially because the process dies out. Clear? Now, let's come to the first model, that is contact processes in random environments of half-plane. Compared with the contact process in determinantal environments, the difference is that here, the recovery rates and infection rates are random variables, not constants. There are many different models. Now let's come to our model. The graph we consider is the half plane, v times v plus. Here we let the recovery rate be constant 1, but we let the infection rates be IID random variables. This is our model. Our main result is this. Suppose the support of mu, that is the distribution of the infection rates. Suppose the support of mu is 0 to positive infinity. Then the complete convergence theorem holds almost assured. This is a joint work with Xinxing Chen. This result is a generalization of our earlier work, which deals with the supercritical population cluster case. In that case, it is a special one because in that case, mu follows the two-point distribution. I just explained the sketch of the proof. We use the Griffiths lemma. that is the complete convergence theorem if and holds if and only if the following two conditions hold. So if we check the complete convergence theorem holds, we just check the two conditions.
Well, could you go back? I just want to see the second. I didn't get to see the second condition yet.
You mean the second?
Yeah, I was reading it when you changed. Okay, thanks. It's too fast.
Clear now?
Oh, good enough. Yeah.
The idea is enlightened by the paper written by Mountford and Grimmett in 1990. We call it the BG renormalization argument for short. The idea is to use annealed law and coupling to contrast the infection path, then go back to quenched law. We want to get the quenched result, but in the quenched setting, it is inhomogeneous. So we first consider the annealed law. There are some difficulties. The first one is randomness. The second one is inhomogeneity, because the half plane itself is not a homogeneous graph. And the third one, because we consider the annealed law first, the process is not Markovian under the annealed law, similar to the random walk in random environment. This is a difficulty. Now let me explain the procedure by some simple graphs. If the process survives, then if we start the process with this seed, we call it the seed. That is at time 0. All vertices on this line. Actually, it is not very clear. This is a red line. A red line. If we start with this seed, then with high probability, it can give birth to another seed on this side with very high probability. Then we start with this seed and forget the previous things and start the procedure in another box. So this seed gives birth to this seed, and then gives birth to this seed. And we can iterate this. Iterating this procedure, we can form we can construct the infection path. That is, if we start with this seed in this rectangle, then after many steps, we can generate another seed in another box. The place of the two boxes are fixed. Then we use the renormalization argument. We treat the rectangle as one point and construct the infection path in a larger space. So we can start with this thing, and in the end we can get another seed very near to the original one. So from this procedure we almost prove this one. Not so strict, but just think intuitively. The second one is somewhat complicated, so I omit it. There are some remarks. The first remark is that our method and the result are still true for high dimensions. What I have just explained is the two-dimensional case. It is true for higher dimensions. The second remark is we believe the result is true for the whole space case. Let me briefly explain why we can only get the result in the half space case. In the original BG argument, they form space-time boxes, not just in the space horizon, but in the time horizon. Thanks to the Markovian property, the independence property holds not only in the space horizon, but also in the time horizon. But in our model, since the process is not Markovian under the annealed law, the independence property only holds in the space horizon, but not in the time horizon. So the box we constructed, the boxes we constructed are only space boxes, not space-time boxes. So we can only get the half place result. But we believe the result is true for the whole space case, although we cannot prove it following the original BG argument. It's a pity, I think. Clear by now? The second model is contact processes on some inhomogeneous finite graphs. When we consider the contact process on finite graphs, the problems we are interested changes. Since if G is a finite graph, then the contact process on it must die out. Since it is a finite state Markov process with only one absorbing state. So we are interested in the extinction time from full occupancy. We denote tau the extinction time of the process starting from full occupancy. That is, at time 0, all vertices are infected. Obviously, tau is a function of the number of vertices n. We are interested in the asymptotic behavior of tau when n tends to infinity. There are some known results. For the results on finite subgraphs of the d-dimensional lattice, if lambda is smaller than lambda c, this lambda c is the critical point for the contact process on the whole d-dimensional lattice. Then tau has order log n when n is large, up to a constant. But if lambda is larger than lambda c, then tau has this order up to a time constant. Up to a constant. In the supercritical case, that is in this case, we can see that the process, the contact process, can survive for a very long time. If the time is log n, is of order log n, we don't see it is a very long time. But if the time is of this order, we see it's a very long time. The process can survive for a very long time, then quickly turn to its true equilibrium, that is the empty set. If this holds, we see that the process exhibits metastability, meaning that it persists for a long time in a state that it resembles an equilibrium, and then quickly moves to its true equilibrium, since it is a finite state Markov process with one opposing state. The empty set is its true equilibrium. For the critical case, that is lambda equals to lambda c, the picture is much less incomplete. We can only get the one-dimensional result. That is, the extinction time is between n and n to the power 4. For the finite subgraphs of the homogeneous tree case, the known result is that if lambda is smaller than lambda 2, the process does not exhibit metastability. But if lambda is larger than lambda 2, the process exhibits metastability. So for this problem, lambda 2 is the phase transition point. Now let me introduce our model and our main results. We consider general trees, not homogeneous trees. We fix D and let n tend to infinity. We let lambda n d be the set of all trees with n vertices and degree bounded by d. In the following, we fix d and let n tend to infinity. Simply speaking, in this model, the extinction time is larger than this order with high probability if the infection rate is sufficiently large. That is, lambda is larger than the critical point for the contact process on the one-dimensional line. That is, if lambda is sufficiently large, then the process exhibits metastability. It is a joint work with Thomas Mountford, Jean-Christophe, Mourrat, and Daniel Valesin. Let me introduce the ideal proof. Here is an important lemma. It's a lemma in graph theory. That is, for a tree T in lambda n d, there exists an edge in the tree. If we remove the edge from the tree, then we can get two disjoint subtrees T1 and T2. The size of the two subtrees are not so small. That is, they are both of size at least n divided by d. Then we can get this important proposition. That is, for n large enough, let T be split into two subtrees. We have a tree. We have a whole tree T. We remove an edge. Then we get two disjoint subtrees. We can get this inequality, which set up the relationship between E tau T1 and E tau T2. Then we can iterate this. If we can iterate this and use the regular subadditive algorithmic procedure to get our result. So this lemma and this proposition is the key point. Key points. Now let's come to the last model, which I think is the most interesting model. That is, the contact process is on NSW random graphs. NSW is a short saying of Newman, Strogas, and Wolf, but this is different Newman. The graph is Jn denoted by Jn. Jn is its vertex set and En is its edge set. The vertex set is simple. It is a finite set, 1 to n. The edge set is a random one. We only give the degree distribution. That is, the degree of each vertex is denoted by di, which follows d1, d2 to dn are IID random variables, and the probability of the degree equals to k is k to the power minus alpha up to a constant, where alpha is larger than 1 and the c is strictly positive. They are fixed if k is large. There are many ways to construct the graph if we know the degree sequence. Newman, Strokes, and Watts wrote in their original paper give a simple procedure, that is, each vertex I was issued with di half edges. That is, we know the degree sequence. We first have some half edges. Then we use the half edges to construct the whole edge. These half edges were matched up in a uniformly chosen manner. The known result is that if alpha is larger than 3, then the probability that the graph is a simple one tends to 1 as n tends to infinity. We see that a graph is a simple graph if there is no loops. The loops means that there is an edge from a point to itself. Then it is called a loop. Also, there are no multiple edges. That means there are more than 2 edges between 2 different vertices. If alpha is between 2 and 3, not so. We treat both cases in our work. We consider the contact process on the NSW random graph. First, we generate a graph according to the degree distribution. Then we run contact process on the fixed graph. There are 2 assumptions. The first one is P0, P1, and P2 are all 0. This is to guarantee the connectivity of the graph. The second one is we condition on the event that the summation of d1 to dn is even. In graph theory, it is easy to see that if and only if this summation is even, we can draw the graph successfully. So, if from now on, if we talk about some probability, they are all conditional probabilities, conditional on this event. We can do so because the probability of this event En tends to 1/2 when n tends to infinity. Chadley and Durrett showed in their 2009 paper that when alpha is larger than 3, for any delta strictly positive, the fraction of infected sites in the graph Gn is bounded away from 0 for a time longer than this. If at time 0, all vertices in Gn are infected. This strategy is another strategy, not the same strategy as Professor Shaw just mentioned. They are both S strategies, but that strategy is the one whom Professor Shaw mentioned is Thora's strategy. This one is Xinxing strategy. 2 different S strategies.
What about Durrett?
Richard Durrett. Only one, I think. Only one, I think. So, we are interested in the fraction of infected sites at this time spot. Given delta between 0 and 1 and lambda strictly positive, we choose a vertex in a random way. We define rho n lambda delta to be the probability of this event. We denote by underline rho and overline rho to be the limit inf and the limit sup of rho n lambda delta as n tends to infinity. We call them metastable densities. We are interested in the asymptotic behavior of the metastable densities when the infection rate lambda tends to 0. Intuitively, the metastable densities will tend to 0 if lambda tends to 0. But what's the order? That's the problem we are interested in. So what's the asymptotic behavior of the metastable density if lambda is small? That is, if lambda tends to 0. There are some previous works. Berger, Boggs, Chais, and Sabri wrote in their paper that if alpha is larger than 3, then the metastable densities have this lower bound and have this upper bound. Note that this power is larger c and this power is small c. They are not the same. But they don't say what the power is. Then Chatterjee and Durit improve their results that if alpha is larger than 3, they give the lower bound and the upper bound for the metastable densities. They give the explicit form of the power. But note that the two powers in the lower bound and the upper bound are not the same. Here is the 2, here without 2. So it is not the true behavior, we think.
There is a misprint, right? I mean, it should be minus epsilon on the right-hand side, right?
Should be minus.
Should be minus. Sorry. What we are interested in first is to improve the bounds. That is, find the actual behavior of the metastable density. And the second one is to extend the result to all alpha larger than 2, not only alpha larger than 3. These are our main results. It is a joint work with Thomas Mountford and Daniel Valesin. If alpha is larger than 3, then the lower bound of the metastable density is this, and the upper bound is this. Note that the order are the same for the lower bound and the upper bound. Compare our results with Chatterjee and Durit's results. We can see that the numerator part is like looks like the lower bound estimation for in their result. But in the denominator part we have the log term. If alpha is between 2.5 and 3, then the order of the lower bound and the upper bound are also the same, but they are different. The numerator part are the same, but the denominator part are somewhat different in the power. If alpha is between 2 and 2.5, things are different. We can still get the same order for the lower bound and the upper bound, but its form is different from the first two cases. So for the metastable densities, there are two phase transition points. The first one is 3, and the second one is 2.5. I just introduced the basic idea of the tools. A very important intuition is that the Newman-Strogate's Walsh random graph is locally a Gaussian tree. That is, if we look at the Newman-Strogate's Walsh random graph, if we start from a randomly chosen point and look at the graph in a fixed number of steps, k. If we fix k at first, if we look at the graph in k steps and let the number of vertices tend to infinity, then it looks locally like a Gaussian tree, but following side-biased distribution. The most important is that the number of steps k is fixed, and we let the number of vertices tend to infinity. It is a very important observation. From this observation, we can use the contact process on Gaussian trees to estimate the contact process on NSW random graphs. We can give a lower bound estimation for underlying row and give an upper bound estimation for overlying row. We use these two estimations in three different cases. The first two cases, that is the case alpha is larger than 3, and the second case alpha is between 2.5 and 3. The procedures are similar, but the details are different. We consider stars, that is the vertices with large width. In the third case, that is alpha is between 2 and 2.5, we use a different idea. In this case, the proof is easier compared with the previous two cases. The idea is to compare with branching processes, so we get a different form of bounds compared with previous two cases. That's all of my talk. Thank you very much.
Any questions?
I have a question about the first part of the talk, about the contact process and the half plane. So you pointed out that the reason that you're restricted to a half plane is because something like the following: you're using the Bezuidenhout-Grimmett results, but in Bezuidenhout-Grimmett they look at the process in space-time. So in that situation, a full plane in space-time looks like a half plane of space-time. I mean, a half of.
Yes.
But you're restricted to looking at the spatial part, and so things are, there's difficulty in going from a half plane to a full plane when you're just in the spatial situation. So this reminds me that the Bezuidenhout-Grimmett results were a kind of extension of slightly earlier results that were done by Barsky, Grimmett, and myself, and we were doing not contact process but just ordinary percolation, and that's why we had to be restricted to a half plane. But those results were later extended by Grimmett and Marstrand to a sort of a full plane or a full space by using some sprinkling technique. So I'm sort of wondering whether the improvement that Grimmett and Marstrand did beyond the results that Varsky, Grimmett, and I had done using the sprinkling method, I wonder if that could be used in your situation to improve from a half plane to a full plane. It's a rather complicated question.
I will try it. The difficulty is because we first consider the node, the average law,
Right.
and the process is not Markovian. So in the time horizon, since the independence probability will not hold. But in the population model, I think in every direction there are some independence. I think. I'm not.
So, yeah, I'm not sure.
I'm not. Thank you very much.
Other questions? If not, let's thank the speaker again.